Welcome to Pomodoro Joe for Sunday, April 30th, 2023. Today we're doing LeetCode problem 1579. Remove max number of edges to keep graph fully traversable. This is a hard problem. Alright, so Alice and Bob have an undirected graph of n nodes and three types of edges. Type 1 can be traversed by Alice only. Type 2 can be traversed by Bob only. And Type 3 can be traversed by both Alice and Bob. Given an array edges, where edges index I is equal to a type, and then two nodes u and v, represents a bidirectional edge of type between nodes u and v. Find the maximum number of edges you can remove so that after removing the edges, the graph can still be fully traversed by both Alice and Bob. The graph is fully traversed by Alice and Bob if starting from any node they can reach any other node, or all other nodes. Return the maximum number of edges you can remove, or return -1 if Alice and Bob cannot fully traverse the graph. Oh man, and then there's this example here. So we have a graph of 4 nodes. Now, it's hard to read here, but type 1 is red, type 2 is green, and type 3 is blue. So type 1 is Alice only. So Alice can go between all the nodes. Blue is anybody, and green is Bob only. So Bob can only go between edges 3 and 4 given the Bob only nodes, but given the Bob only nodes and the Alice and Bob shared edges, then he can go through 1 through 4. Using these blue edges, they're hard to see. Okay, so this is going to be tricky, but we'll work through it. We'll put 25 minutes on the Pomodoro timer and we will get started. So for this one, we're looking at essentially two separate graphs. We're looking at the Alice graph and we're looking at the Bob graph. But these graphs actually can share certain edges. So we kind of have these two graphs with some shared edges. I think my initial thought was to break this up into 3 separate pieces: the Bob graph, the Alice graph, and the shared graph. But I think I'll just keep track of the Bob graph and the Alice graph, but we'll include the shared edges in each of those two graphs separately. Now the shared edges, because they can work for both Alice and Bob, they're actually more important, or I would say they do twice the effort of all the other edges. So a shared edge, since it can be traversed by both Alice and Bob, is worth more than an edge that only Alice can traverse. So for example, this edge between 1 and 2, there's a shared edge, there's also an Alice only edge. Now we don't really need that Alice only edge. If we got rid of the shared edge, then we would have a problem because Bob wouldn't be able to traverse these two nodes. But if we get rid of just the Alice edge, the Alice only edge, then both Bob and Alice can still get between nodes 1 and 2. So these shared edges have a greater weight or a greater importance. They do twice the effort or twice the work that the other edges do. So we'll keep track of the shared edges and we'll keep as many of them as we can. Then we can try to get rid of some of the other edges that might be duplicates of these shared edges, like this one for Alice between 1 and 2. All right, so with this, we will start with some result. And I'll set it to -1 to start with, and we will return the result at the end. First thing I'll do is sort my edges. Because I know these type 3 edges are more important, we'll want to process those first. So essentially what we'll be doing is building up these graphs, one for Alice and one for Bob. But we want to build in all of these shared edges first because they can be used for both graphs. So we'll be traversing or processing our shared edges first, and then we'll go through and process the Alice edges and the Bob edges. So I'll want to sort these edges, and then we'll start processing. So we'll sort them. I'll have a sorted edges. That's just going to be sorted and edges. And in this case, we want to sort essentially in reverse. We want type 3 edges to be first in our list. So I can do a key equals lambda. And since I want the type 3s to be at the beginning, I actually need to do a -x of 0. So x0 gives us the type because it goes type node node. So x0 gives us the type. We want type 3 to be at the beginning of our list. So if we do negative type, meaning -3, that will give us all of our type 3s at the beginning of our list. All right, so that's our sorted edges. Next, this is where we get into a little bit more complicated stuff. In this particular problem, we're trying to create two subgraphs, one for Alice, one for Bob, and we want to make sure that all of these nodes are included in both graphs, both Alice's graph and Bob's graph. In order to do that, I want to find groups of nodes. And a great way to do that is to use a union find. A union find is a great way to optimize grouping things together, grouping similar things together. In our case, we'll be grouping connected nodes together. So anytime we find two nodes that are connected by an edge, we put them in the same group. If we find two other nodes that are connected by an edge, we'll put them in the same group. But if we have two groups that are then connected by nodes that are connected by edges, we want to merge these two groups together. So the union find will actually provide an optimized way of grouping these similar or connected nodes together, and then being able to merge two groups of connected nodes together. So I'm going to create our union find class, and actually I will do that. I guess I'll do it internal. So in the union find class, we will have three functions. We'll have an init, we'll have a find, and we'll have a union. I'm just going to call this node groups. Okay, I will explain this in a minute, but I'm going to go on and stub out the rest of the union find here. Okay, so in this we have our init, we have our find, which takes the node that we're trying to find, and we have the union, which will merge two groups of nodes. Okay, now initially, all of our nodes are going to be in their own group. So we'll have this n length array, or in this case, it's n+1 length array. The reason why I'm doing n+1 is because the nodes are labeled from 1 through n, and we want to have enough space for all of these. So our list here will be 0 indexed, which means that we'll have this one extra 0 node that doesn't really map to anything. Otherwise, the node numbers and the index into our list here will be mapped, and that's why we're doing this n+1. Now initially, all of our nodes are in their own group, so they point to themselves. So the index will be the node, it's the same as the node number, and the value at that index will be the group that it's in, or the parent node of that group, or root node of that group. So initially, all of these groups are going to be individual nodes, and they're grouped to themselves. So their parent or their root node is just the same as their index. That's why we do it this way. Now when we merge groups, then we'll start merging or changing these values so that we can merge two groups together. And I'll get to that later. So we have our init, now we have to do a find. So as I mentioned earlier, each of these nodes in this node group, the index is the node number, and the value is the root of that group. It's the root node of the group. Initially, each node is its own group and it points to itself as the root. But if we want to find the root of a group, we just look for a node that points to itself. So in our find here, if we find a node that points to itself, we've found the root of our group. If the node doesn't point to itself, it's pointing to another node in the group, which then will point to another node in the group, which will keep pointing on up until we do reach the root of our group. So we can just do something like this. So if the node is not pointing to itself, we know that it's not the root. So we need to traverse up and find the root of this group. All right, so as long as we don't have the root, we'll just set our node equal to the next node's parent node, and so on and so forth until we reach the root and we can return the root. Now there is an optimization I can make here. If we need it, I'll come back to that and do that later. Now the union, this is where we merge two groups together. So with this, we'll just find out which groups we have so far. So I will find the group that both node 1 and node 2 belong to. And if they're the same group, then we're done. These are already the same group. We don't need to union anything. If they're not the same group, we need to merge these two groups together. So there are many different ways to do this. I like choosing the minimum group as my parent group. So that's going to be the one that the larger group gets merged into. I shouldn't say larger. The larger labeled group gets merged into. So I have my group that I'm merging into, and I have my merging group, which is the group that I am merging into the main group. Maybe I'll call this main group. So I have my main group, which is, I'm just choosing arbitrarily to use the minimum of our group 1 or group 2. And then we have our merging group, which will be the other group. So it's group 1 if group 1 isn't the main group, otherwise it'll be group 2. And to do the merge, well, then we have to say our self node groups. So we're going to grab the root essentially of our merging group, and we're going to point it now to our main group. So this is kind of like a linked list where you're repointing the head of a linked list. You're merging two linked lists together. You're taking the tail of one linked list and you're pointing it to, or actually in this case, it's more like you're taking the head of a linked list and you're pointing it to a head of a different linked list. So this should handle our union find class. We have our init, our find, and our union. Now, how do we use this class? So we've got our sorted edges here. We'll need to keep track of the Alice subgraph and the Bob subgraph. So we'll have two subgraphs here. Let's see, I'll just call it nodes. So it's going to be the union find, and we have to pass in how many nodes we're expecting to be in here. So we pass in n. So now we have these two union finds, or two subgroups or subgraphs of nodes, the Alice nodes and the Bob nodes. Let's see, what else do we need? Well, let's keep track of which nodes are in which groups. So, or I should say which edges are in which groups. And let's also keep track of how many edges we are not including in groups. Do we really need to do that? Yeah, I think we do. So these are going to keep track of some stats on which edges we're including and which edges we are ignoring. Now we need to go through all of our edges. We're using our sorted edges here, so all of our type 3 or shared edges will be first. So for our edge in sorted edges, in fact, I'm going to break this out into our type, our node 1 and node 2, or A and B. All right, now we check the type. If we have a type 3, in this case, we'll handle it one way. I'm just going to say pass for now. Otherwise, if we have a type 2, these are going to be the Bob edges. Otherwise, we have a type 1, which will be the Alice edge. I believe that's right. Is that right? Yeah. Okay, so if we have a type 3, well, we'll need to add this to both the Alice and the Bob groups, if it's not already there. So first, let's check to see if it's already in one of them. Since we'll be adding these to both Alice and Bob, we don't need to check both of them. We just need to check that one of them has it. So we'll just find node A. Now, if that's in the same group as the Alice node for node B, so if these are in the same group, we can ignore this edge. But if they're not in the same group, so let's do that one first. So if this node, if we find node A in Alice and find node B in Alice, if they are not connected, they're not in the same group. So remember, this find will return which group these nodes are in. If they're not in the same group, then we need this edge. So we're going to include this edge. So we just call Alice nodes union A and B. We're going to merge these two into the same group. We need to do the same with Bob nodes. And at this point, since we're using these edges, let's record that in our counts here. All right, now if this edge is already covered or these nodes are already in the same group, we actually don't need this edge, so we'll count that in our removed edges. So this takes care of the type 3. This is the Alice and Bob shared edge. And basically all the others, the type 2 and type 1, are basically similar here. So for this one, type 2, this is the Bob only edge. So we'll just check the Bob nodes. And we don't merge the Alice nodes at all. So if the Bob nodes, A and B, are not in the same group, then we'll merge them. We'll union those into the same group. And we'll record that on the Bob edge count. Otherwise, this is a Bob edge only. He's already got these two nodes connected, so we don't need this edge. Let's remove it. And we can do the same for Alice. I'm just going to give this a little bit of space. We can clean that up later. Okay, so this should actually handle the majority of our work. It's a lot of code here, but it should do what we expect. Okay, now the last piece of this, we need to return something. So in our case, well, we're keeping track of all these edges that we basically processed but didn't end up using, so we can just return those edges. So removed edges count. I should probably call it removed edges count. Yeah, I'm renaming this removed count. All right, so at the end here, we can just say, these are all the edges that we've removed, but we need to make sure that the other graphs, like the subgraphs that Alice and Bob have, are actually complete. We need to make sure that Alice and Bob can still reach all of the nodes. So how do we check that? Well, we know how many edges they have, and we only included edges that they needed to connect nodes. So basically these unions, or these counts, will be the number of edges in each graph, and those edges were all required, so there are no extra edges connecting nodes more than once. So how many edges do we need in a graph? Well, if we have 4 nodes, we need 1, 2, 3 edges. If we only had 2 edges, it wouldn't be enough to connect all the nodes. If we had 4 edges, that's more than we need. So we really only need n-1 edges to connect n nodes. So let's check to see if both Bob and Alice have n-1 edges. Otherwise, we return -1. So here we go. We are down to very little time. So let's just run this and see if we can pass. I'm sure there'll be typos. I'll correct those and we'll move on. Whoa, it actually worked. I'm a little bit shocked by that. Okay, let's submit this and see how we do. We have a wrong answer. All right, so we'll keep this test case. Let's take a look here. Let's run this again. Looks like it was returning -1 when it should have been 114. Okay, so we're saying they weren't traversable even though they really were. Let's see what we're missing. Oh, this is my problem right here. This should be a while. I'm surprised the other ones actually worked. Yeah. Oh, wow. I'm surprised that the other solutions worked. Okay, so this should be while this node is not the parent of itself. So while we're not at the root node. Let's try that one more time. Okay. That makes a lot more sense. Let's submit this and see how we do. And we have a time limit exceeded, but we do pass 82 out of 85 test cases, so we do pretty well. Now with the time limit exceeded, I think I will have to jump in and do a couple optimizations here. So one thing we can try is changing this min. Let's do our own min, which can be a little bit faster. All right, so let's try that. It might make a difference, probably not. All right, still not enough. All right, so this is where we jump into this optimization I mentioned earlier. So this one, we're just saying, while this node is not the parent of itself, we'll keep tracing up the line until we do get to a node that is its own parent, and that's the root node. But one thing we can do is, instead of just going one at a time, we know that this node n is not the root. So we can go to the next node and see if it's the root, or we can go to the next node's parent and see if it's the root. So we can basically jump two at a time instead of doing one at a time here. So let's try that. Oh, and in fact, what we can do is we can repoint some of these. So we can redirect, let's see, this guy to point to the parent, which should save us time in future finds. And then we still need to update our n. Okay. So this is an optimization. Hopefully it will help. Let's see, that's not, I have. Okay, I think that should do it. So this is basically taking, you can imagine this as a long chain of nodes, one pointing to the next. Now in this case, we're collapsing that chain to say, instead of having this long line of nodes, we're condensing them into more like a central node with a bunch of nodes that point to that central node. And that passes. And we do pretty well. We have 71% for runtime and 18% for memory. Not too bad. I am way over time on this one, my apologies, but it's worth doing. This one is super tricky. Union find is a great data structure. I recommend checking it out. I'll leave a link in the description. Yeah, hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.